which is oh, one more thing I should say. No, never mind. Okay, in our design process, let me make some assumptions. Let me state some assumptions. Single cycle assumptions. Obviously, how long does every instruction take in a single cycle architecture? Yeah, one. But I have to ask this because on the final, people often get this wrong. All instructions take one cycle. That's kind of obvious. I don't need to write it down, but I mean, just read it. Okay, last time we mentioned that we talked about clock circuits, and we said sequential elements are written on the rising edge. We're going to so what does that mean? That means typically at the end of the cycle, we're going to write a sequential element, whether it's a register or a memory. At the beginning of the cycle, we're just going to be reading all our sequential elements, again, whether it's a register or a memory. So how do we figure out the clock cycle time? The clock cycle time, it has to be long enough. However, it says in microsecond or picosecond wise, it has to be long enough to account for the longest path to our circuit. So after we're done designing the circuit, we're going to do some analysis and say, if you take this path through the circuit, it's going to take 8 nanoseconds. If you go this path through the circuit, it's going to take 11 nanoseconds, or so on, whatever the number is. And then say that pick the longest path of them all, and say the clock cycle is going to be longer than that. So we're going to set the clock cycle after we do the design. Clock cycle is long enough for longest path through CPU. And this path is called the critical path. Okay, so that's what we'll do, and again, sequential elements. The sequential elements we're going to have are a program counter, the register file, and data graph written on rising edge of clock. Note, I did not say instruction RAM because we're not going to write the instruction RAM. We're assuming that we're making some assumptions. We're assuming that the linker loader, the operating system, is the only unit that can write the instruction RAM, and we're not going to design that happens magically. We're assuming that program is already in instruction RAM, so we're not going to worry about that. So if we were to worry about that, then we'd have to worry a little more about timing because the instruction RAM also gets written. But in practice, how that would be done would be that's itself a program. The linker loader is a program, and we would have some way of writing the instruction RAM. But we're not going to worry about that. So we're just assuming that the program is just stuck there, and somehow it got there, and it's not going to change. Okay, so now we're ready to write code, design hardware. Okay, I'm going to suggest one way of doing it, which is I find that a lot of students do good if they follow this recipe. So when we design the hardware, what I'm going to do is I'm going to write it in English first. And we have to be very precise because English is not a precise language. Natural language is not precise. But we write what this fetch, decode, and execute do very precisely in English. And then I'll tell you what we do next. Okay, so designing fetch. So what is a fetch? Fetch, let me put that so that what does that mean? That means you have to read what's in the PC register, a program counter. Then PC contents to the instruction RAM. Oh, hold on. Let me. Are they calling it the program RAM or the instruction RAM? Yeah, instruction RAM. Instruction memory. Read address. By the way, I will often write R and W just for shorthand. In the book, they call it read and write, and all the figures from the book, they call it read and write. But I'll call it R, and the same for IND. I'll call it IND instead of instruction and data. In the book, they spell it out, instruction and data. Okay, so we sent the address, and what do? Then we tell the memory, hey, I want to read something. Read IRAM, and we get the instruction into the CPU. And in addition, one thing we're going to do at this point is what is the next instruction that's going to be executed? The address of the next instruction is going to be PC plus 4. So we might as well set update PC to point to the next instruction. So we're going to do that as part of fetch. I mean, technically speaking, we could say we could do that later, but we're going to might as well do it now. Add 4 to PC. Okay? Now it's going to be super easy to design this. Okay, now comes to what I'm going to suggest as your method for design, because people have problems otherwise. I'm going to suggest that the first thing you do is you underline sequential elements. What are the sequential elements in here that we need to underline? You see the purple looks like blue, green, red. So PC is a different red. So PC is a sequential element. Any other sequential elements? Good, IRAM. Anything else? Well, that's a port. That's a connector to the RAM, so that's not really a sequential element. And what did you say? Somebody say something else? Yeah, that's pretty much it. Okay, so those are sequential elements. What are combinational elements here? I'm going to put a box around. Maybe I'll put a box around the sequential element because they sound more important. What are the combinational elements? Combinational elements do something. They're basically, you take some operands and you do something. So which word here corresponds to combinational elements? Add, yeah, sure. Add, I'll just add, you can do add 4 if you want. Anything else? Well, read is not really a sequential element because it's a function done by the memory. Yeah.
Is the CPU
not really, because the CPU has memory. But it's really just to add. So add is the only sequential element here. I'm sorry, only combinational element here. Okay, so now what we can do is we can design this circuit to do this. So let's do that.
The CPU has sequential element?
No.
I'm going to have an instruction memory.
It's made up of sequential elements, I guess. Does that make sense?
And it's going to have a read address. And it's going to have data coming out of it. Actually, we're going to call it instructions coming out of it. Okay, so that's this sequential element. We have a PC. I'm going to draw that right here. That's that element. So PC and IRAM are the two sequential elements. We need a combinational element, an adder.
Yeah.
And I'm going to draw that. The reason I'm looking somewhere else when I do this is I want to make it look the same way the book has it. I'm gonna make an adder there. We could write ADD or you can write plus, it doesn't matter. So what I did is I looked at the sequential elements in my precise English, and I wrote them here. And at this point, you should know all the force in every sequential element and every combinational element, so you know the names. So I just got through all of them, and now I can just connect things. Send the PC contents to the IRAM address. How do I do that? I connect this to this.
Because she's already reviewing this content for us.
Get it ready.
Okay, so send the PC contents to the IRAM address. Read the IRAM to the CPU. And, well, that's gonna go here. But we're not gonna finish that because that's gonna go elsewhere on the CPU. Everywhere here. So we're done with that. Add 4 to the PC. How do we do that?
What's on this too?
We connect this to this adder.
At the same time, I can let me check.
And we bring in a 4 there. The reason 4 is just a hard-coded value. Remember, these are 32-bit ports. So this 4 just corresponds to whatever the binary value of 4 is, those zeros and ones. Those 32-bit zeros and ones, it's hardwired to those 32 wires coming in here. So we can always bring in hardwired constants because it's just connect this input to a 0 or connect it to a 1. So we add that to 4. Add 4 to the PC. But I'm adding it to the PC. Here I'm producing it, but I'm not adding it to the PC. So I have to take it back and store it back in the PC. And I'm going to use a slightly different color because we'll erase this later. So I'm going to the yellows will be erased later when we make things more complicated. Okay, so we're done designing the fetch. Okay, so it's that easy. Anytime you want to design, write it in English, identify the sequential elements, identify the combinational elements, and then connect them up exactly the way you roll. The hard part is not doing this. That you can train a chimp to do this part. The hard part is writing this. Well, a very smart chimp. Maybe not. Okay, so let's do. I told you decode is going to be very trivial. So let's start doing the execute. So I'm going to take this off, and I'll bring this back later. So execute for R-type. What is an R-type instruction? What is an R-type instruction? An R-type instruction, it takes 2 register operands, it does something to them like an add. I'll use add as my example, but it could be any R-type instruction. It adds those 2 registers, and it stores the result in some in a 3rd register. It could be one of the same registers, but it stores the result in some register. Okay, where are registers going to be stored? I already told you that the sequential elements on the single cycle MIPS are going to be the program counter, the register file, and the data RAM. So the instruction RAM. So the register file is going to be contain the registers, the 32 general purpose registers. Okay, so now we can do this. First step. I already told you what the first step is going to be. Read 2 registers, operand registers from the register file. Read 2 operand registers from the register file. And we know, because we are in the machine code, we know that the bits, whatever, I'd have to look it up, but bits 15 to 11 or whichever bits contain one of these operands. And some other bit field contains the other operand. So we know exactly how to do that. We'll do the circuit design in a few minutes. Process, now that you've read those 2 registers, you can process them. Process operands. Where do we process them? the R type instruction is going to be an and, a subtract, an add, a subtract, an or, an XOR, something like that. So that is going to be done by the ALU, the arithmetic logic unit. So it's going to be processed in the ALU. The ALU does all your integer operations. And we're not talking about floating point. What do you do with this result? Now you have x plus y. If you have x and y as two operands, you stick them back in some register. Store result. Let's just say ALU result. Store ALU result in the destination register, which is in the register file. Okay, again, we're very good about writing good English, but once we write the good English, it becomes trivial to design. So now we're going to design it. What are the sequential elements in this English? Good, RF. Is that a sequential element? No, it's not. What are the sequential elements? We're done. That is the sequential elements. So now, what are the combinational elements? Store is not a combinational element. It's not. Yeah, ALU is a combinational element. Store is something we're doing. It's not. It doesn't correspond to any particular combinational element because it's a function of the memory. So it's neither a sequential element nor a combinational element. It's something the memory does. Okay. Any other comments? Yes.
Do you have like a basic definition of combinational element?
Yeah, that is what we did either last time or 2 times back. It's something which takes 2 inputs. It's also basically 160. It's something which takes 1 or more inputs and produces an output. And there's no clock to it, so there's no timing associated with it.
Do you want me to send it to you later?
No, I'm actually paying attention.
Sequential is something with memory. Yeah, you want to go back and look at the slides because that was the kind of the main point of the slides, where we split up elements into sequential elements and combinational elements. Or look up your 160 notes. Okay, so now we can design. We can modify our design to also execute R-type instructions. So let's do that. Yes.
So we say read to register from R. Are the registers being stored registers?
No, the registers are in the register file is a sequential element. They're there. So the previous instruction would have done it. I mean, previous instruction didn't need to do it, but then you'd be doing garbage. So that's up to the programmer's free to write garbage. As far as this add instruction is concerned, you're reading whatever is in the register file.
Oh, I'm so smart.
You don't care what's in the register file.
Heck yeah.
You're not the programmer. Okay.
What?
So let's draw the rest of part of the rest of the design. So I'm going to draw the register file somewhere around here, and our register files have 2 read ports and 1 write port. So the 2 read. Remember, a read port you send the register number and you read what's stored at that register. We're going to call the read port read register 1, read 1, read 2, and we're going to call the write port write register. And those are effectively the addresses. And then we have the data. The data that we're going to write is going to be called write data.
Wow, you can read.
And the data that we read is going to be called read data 1 and read data 2. Okay. So that is our register file. That's our sequential element. And now we get to connect stuff up.
What does it say on W what?
Okay. So
W,
read
right
2
register,
registers
and
from the
then
register
right
file.
I think data.
Oh, that's just
Okay. Oh yeah, I have to render on the ALU. The ALU. Process the operands in the ALU. So this is going to go to the ALU. And I'm going to do this one in yellow because I'm going to later erase it. Well, not physically erase it, but strike over it. But for now, that is also going into the ALU. So I processed the trigger, I read the two operands from the register file, and I processed them in the ALU. And I'm going to send the ALU output somewhere. Store the ALU result in the destination register. So I want to store the result. I want to send the result to which input port of the RF. The read address 1 and the read address 2. I'm sorry, read 1 and read 2. They are not about reading. I want to write to the register file. So I want to write it to write data. This is the 32-bit line. It's producing 32 bits of the result, which is data. It's not producing the address of the register, which is a 5-bit line that picks one of the 32 registers. So it's going to be connected to this. And that one I am going to, okay, so that one I'm going to put it in yellow, but even though I will, well, those you'll see later. Okay. Yes. Right, register, REG. Actually, you know what? I'm going to be more consistent with the book.
Yeah.
I'm going to call this read register 1 and read registers 2. Okay? But that's not what you asked, but I'm also going to do that. Okay, are we done with the execute for archive? Yeah, I guess we are. Because we've done this, and we've done this.
what do you need?
Now we're ready to do the execute of more instructions. Let's do load word. If you have questions, now would be a good time to stop me and ask questions because it's quickly going to. Okay. Yes.
Well, no, you wait, no, one section. Are we, just for right now, are we gonna, like, start connecting these soon?
Oh yeah. Everything's will be connected, and eventually we'll get this. Yeah, I don't either. But I'll figure it out.
He showed a big ass circuit he's gonna draw. Showed a big ass circuit he's gonna draw.
Well, decode is going to be trivial. We're going to add it. It's basically, it'll be really trivial.
No, there's no connection there.
No, you don't need to design it in the order of the instructions happening.
No,
You design it in any order you want.
circuit, right?
he just said V
Okay, so
code.
the execute
He
for
said
the load word.
V code. Not D. V. Like the, but just V. You pronounced it. Yeah, V code.
So I'll write out the instructions. So the load word is the RT
I thought we
offset
were done with
Yo, I
this.
got my connection with my time.
RS. Remember
Yeah.
that this offset is 16-bit. I'll write it out.
There's only pencils there. I was just
16-bit
them too.
complement. So it's a 16-bit offset. So we have to do stuff to it. We'll talk about that. Okay. So what happens in the load word? What is the very first thing that we do in the load word? We take this and we add it to this, right? Because we want to compute the address that we're sending to RAM. So we have to add this and this. Not exactly, but approximately we have to add this and this. So let's write that.
What did you write?
It's the same thing.
16-bit 2's complement. PC. Add. I'm going to leave a little space here intentionally. Offset and let me write that. And register
You can call it wrong.
RS in the register file. Now, why did I leave some space there? The offset is 16 bits, and the register file, and the register is 32 bits, so you have to do something to the 16 bits to make it a 32-bit number. And we know that this number is going to be 2's complement. So how do we convert a 2's complement 16-bit number to a 2's complement 32-bit number? We do a sign extended. So, sign extended.
Lock in, bro.
Offset and register RS in the RF. Yes.
Oh, he can hear the audio. He can hear the audio.
Because that's our
Nah,
machine code
this is
format.
not recording screen. This is recording everything.
That's what we've been doing this entire
Yeah,
semester.
yeah,
This is 16. Why?
And remember, because we have to make it less than 32, otherwise the instruction won't fit in one 32-bit word. We use the entire 32 bits for the offset. All are immediate for 16 bits. You're very lucky that that was in my, when I was making the test, that was one of the questions I did not include. That was one of the questions I originally had. So you lucked out. No, I told you now, I'm not going to put it in the final. Besides, the final is not different. It's all hardware. It's all design. Okay, so we add this address. What do we do with this address? You have a 32-bit address. Well, what is it addressing? Memory, yes. So we send the address. Send result
Okay. Damn.
to the, this is the data RAM. To the data RAM
Interesting. It's right there.
address input. And then what do we do? When we're doing a load word, we're going to read that memory. And where are we going to read it to? We're going to read it into RT, which is in the register file. And send result to register RT in the register file. Okay, now we do our usual business. We identify our sequential elements. What are our sequential elements? Well, yeah, all right, yeah.
He sent some beats
For
today,
DRAM.
but no, like that. Check your Outlook. Maybe you did it already.
Anything else? No. Okay, what are our combination elements? Add, good.
And?
Sign extended?
Yeah, I guess we could say that. I'm going to put that in underline, and I'll tell you why in a few minutes. Yeah, I'll just underline it. It's just that. But I'll tell you why that's kind of fake anyway. In a few minutes. Okay. So we can add this to our circle. So let's see. Let's try not to make too much of a mess. Eventually, I think I'll have to go to a different diagram because then it's just too messy. Okay, the register file is already there. The DRAM is not there. So unfortunately, I ran out of space. The DRAM, I'm going to draw it like down here. No, actually, yeah, let's do it like this. Let's see if this works. We'll need a little effort by me to get it right. But
And then he did like a dotted underline on the sign extend. He said it's kind of like a fake one though.
there's the data RAM, and it has an address input. It has a write data. Next, I'm going to slide it over for now, and it has a read data. Okay? And we're going to ignore the PC part for now. Yes. I don't know if this the exact diagram is on the book. They have a final diagram and they have various intermediate diagrams, but I don't know if this exact one is on the book.
Are you driving the one that you're looking at? The one that you're copying from?
we have an offset which is coming from, where is it going to be coming from? It's going to be coming from some field in the instruction. If you look at the machine code format, it's going to be coming from bit 0 to 15 of the machine code. That is where that offset is stored. So we're going to branch off from that offset. So we're going to get an instruction, and bits 0 to 15 of that instruction are going to be the offset. And we're going to do a sign extend of that. So we can do a sign extend of that. And so that's going to come in at 16, and that's going to come out at 32. And when we do this, and now I said this is kind of fake. Why is it really fake? Because we're taking 16 wires and just copying one of those wires 16 more times, the sign bit. The most significant bit, that's what a sign extend is. Yeah, you take the most significant bit and make 16 more copies of that. So it's not like, there's no transistors in there. It's just some wiring magic, some wiring tricks that we convert the 16-bit value into 32-bit value. So even though we could say it's a combinatorial element, combinational element, it's not really a combinational element. It's just some wiring tricks. Okay, so now we have a 32-bit sign extended offset, and we have a register. Again, we look at the machine code, and we check whether, later on we're going to say one bit field in the machine code is going here and one is going here. And the one that is going to contain the register RS happens to be, I'm cheating now, happens to be read data 1. So read data 1 gets here, and this one has to go into here. Okay? So we send this one up. Well, first if you remember, no, hold on. Yeah, that's not as good. So if you remember, this one has to go into here. So what we can do is, I don't want to mark this up because I'm going to erase it later. So I'm going to, you can make a line like this. How about you do this? You can make a line like this, and we can make another line like this, and connect that. So assuming these are lines, we can connect this into this ALU, right? Everybody happy with that?
No.
Why not?
You can't have two outputs go to the
Yeah,
same.
exactly. We just burnt the chip because we're connecting this output and this output together. That is bad. So we can't do that. But that's what we want to do. We want to connect this into the ALU. Well, it's not really what we want to do. What we want to do is we want to connect either this or this into the ALU. One thing I want to mention at this point is when we design, we split up our design into the data path design and the control design. The data path is making sure every path exists to support your ISA. The control is making sure that the correct instructions are executed. So the control says which paths are exercised. The data path just gives you all possible paths. So what we want is we want to pick either this or this, which means we need a mux there to pick either this or this. Which is why so now you can ignore all this yellow stuff. Everybody got that?
Yeah.
Okay, so we're going to make a mux. And that mux is going to be right here.
Read the final.
Maybe the 160.
And
Okay, maybe not 160 final. I forgot how to do
Zero.
something.
that's going to be 1. So the 0 is the 1. This is going to go into the 1 input of the mux. And what used to be coming out of there is going to be going to the 0 input of the mux. Okay?
This looks like
So now we combine well, we're not done yet, but we combine the execute of the load word and the execute of the R type.
360.
Oh,
Yes.
360 more less than
Sign
this.
extension is going into the 1, and the read address 2 is going to 0.
Yes.
there's game design next mostly.
And the read
What am I
data,
doing next?
read data.
I'm not
So
doing
read data
that.
is going to go into 0.
Recording.
Okay, so now we, well, that's the first
Then I
line
need to
of,
get rid of matrix.
that's the first line, because the add is going to be done by the ALU. Now we want to send that result of the ALU to the DRAM address input. Well, that should be easy enough. The ALU result
Take matrix with me next
goes to
semester.
the
You didn't take
DRAM
matrix yet?
data input.
Oh, you're a bum.
Alright.
Read the RAM and send the result to register RT and RF. And that is, if you look at the machine code, register RT is going to be mapped to these bits.
Person in that
So I want to send that to
God.
connect that to this yellow line. But once again, we have a problem. We're having this yellow line that goes there. We also want this to go there. We cannot connect the two outputs together. Everybody see that? Because the R type, we have this being written to the register file. In the load word, we have this being written to the register file. We cannot have both being written to the register file. What do? We can't connect those two together. What do? Mux again, good. So let's make a mux.
Oh, okay. Not too much now.
And we are going to call this one input 1 and this one input 0. And input 0, forget this yellow. This yellow no longer exists. The ALU, I'm going to send it around to input 0 and bring that around. Into the right data. So yellows no longer exist. Okay, so mentally strike this out. If you didn't write it down, you can strike it out physically. So now we have the load word and the R type done. Yes.
Okay, so from the ALU, you put it into
Let me
and then
pull it up.
read data, you also put that into the box, and then you put that in all.
Right. So we're picking either the ALU output for the R type, or the load word output for the the RAM output for the load word instruction.
Register file.
Yes. Because both of them write the register.
It's on top of
Okay, so now we have load word. Okay, let's do store word next. I think you see where this is going. Execute store word, and that is going to be called $RT offset $RS. The first line is the exact same as load word. Add signed extended offset and register RS in RS. Second line is kind of the same. Send result to DRAM address input. I said kind of the same because not only do you have to send the address, because you're doing a store, you also have to send data. Well, what is the data? You're going to be sending the data in RT. And contents of $RT in register file to DRAM data input.
I don't have it on my phone right now. Why?
And
I'm sure you're on.
I told you we're going to do data path and then control path, but I'm going to cheat a little and I'm going to do rule control.
both.
Tell, well, instead of writing tell, I'll just say send one on DRAM write control. I mean, strictly speaking, well, not strictly speaking, this is not data path, this is control path. But we just, but I just don't, I just feel like I'm incomplete if I don't mention that here.
I'm sure the big unit is just like.
By the way, our book calls it control instead of control path. I will call it control path because I think that's more standard. No big deal. Okay, so the sequential elements are the same as before. RF, DRAM, DRAM. Combinational elements are same as before. Only difference is that we're going to add one more path to send RT to the DRAM data input. That's the only difference from load word to store word. So all the paths for store word already exist.
That's what I just said.
I did not do this underline in your notes, but I'm just pointing it out. All of the things that we've done in the execute have already been done, except
Can I see yours
for
for later?
I think about it.
this line.
Yes, ma'am.
Okay? So that is what we have to add to our design. Yes?
How do you know, like, when you have to go too far as opposed to, like, get data?
It's only 6:25.
What do you mean?
Like,
Well, we know what the assembly language instructions do. So that's why we wrote this down.
Really? Where?
Yeah, we have to know the assembly language. You have to know the MIPS ISA really,
New
really
York or
well.
New Jersey?
Yeah.
That's what he
Is
does.
that your question?
yes.
Yes, yes. You have to know it really, really
Should
well.
know it.
Which is why a lot of people do much worse the second half of the semester than the first half.
How much does it cost?
Okay, so we need to,
I know,
now we
it's a
need
few
to
hundred
discuss
at least.
the contents of RT.
Almost like 1K.
Only 1,000, bro?
Whereas
Wait, did you do it again? Last
Going
time?
all the way in the back.
Okay, the contents of RT are going to be coming out, I'm telling you, you have to trust
That
me.
is not
I'm going to be
1,000
coming out
a lot.
read data 2 in the register file. So let's,
Oh, that down.
so coming out of
You got
here,
that from me, bro?
I got you.
that is also good, that is going to go to the right data input. So now we finish the store word. Okay? So we're gonna do the branch next.
How are we telling once which register data?
That is control. We're not doing control design today. We're doing that next time. Because the control will say, we'll figure out which one of these paths is actually exercised. Okay, so now I'm going to go on and do the branch.
Technically, nothing. It's the mix I had to do. Some people could think
I'm only going to do branch and equal. Because the book only does branch and equal. Branch and not equal is a very trivial modification.
Not one crack.
And I shouldn't say modification, it's a very trivial addition to this. So what is branch? It is, it takes two registers, happen to be called RT, RS, and
Cool.
has a destination label. Now I do have to remind you that this label is
I don't hear my thumb.
PC relative
Does that even count?
word offset. So it's not a byte address, it's a word address and it's PC relative. So we have to do, just like we did for the load word and store word, where we have to do a sign extend of the immediate. We're going to have to do some kind of processing to get this into a normal, into the real address that we want. But we'll worry about that later. Okay, so how are we going to do a branch? A branch is good, it's probably the, not probably, because it's definitely the hardest instruction, the most complicated instruction. The way we do the branch on equal is we are going to subtract RT from, either RS from RT or RT from RS, and check if the result is 0. Remember when we talked about ALUs, we said ALUs might produce a 0 flag, which says that yes, this result is a 0. We're going to be using that. So we're going to subtract these two registers, we're going to send it to the ALU, subtract them and check is the result 0. If that result is 0, then we're going to do the branch. Okay, so let's do that. Subtract, and I guess we're subtracting RT from RS. If the result is 0, well, I'll leave an empty line here. No, don't leave an empty line here. If the result is not 0, we do nothing because PC has already been in the fetch phase. We already added 4 to PC, so we're fine. If the result is not 0. If the result is 0, we take this word offset. We have to convert it to bytes, so we stick 2 zeros in the least significant part to convert the word address to a byte address, essentially multiplying by 4. And then we add that to the PC. Shift label offset 2 bits left. Again, the same as multiplying by 2. And add result to PC. Okay. So now we do our usual thing. What are the sequential elements here? What? Yeah, PC, yeah. I just didn't hear you. You weren't wrong. I just didn't hear you. What are our combinational elements? Oh, actually, there's sorry, there's one more sequential element. I did not explicitly write in the RF, but there's an okay. There's an RF for that's where RT and RS are stored. So any other sequential elements? No. So the combinational elements? ALU, good. What? Yeah. Well, subtract is done in the ALU. So it's not that underline it twice. Yeah, shift is one. Again, shift is kind of a fake one. It's just a wiring game, but we'll underline it. Add. That's one. Okay. So let's do it.
There's combinations and sequential elements.
Okay, now it's going to get a little hairy. Okay, this offset is going to be stored in the immediate field. It's going to be stored in bits 0 to 15 of the instruction. If you look at the machine code, that's where it's stored. So bits 0 to 15 of the instruction are going to be actually, we're going to sign extend it first, and then we're going to shift it left. That's just the implementation. We could implement it. We can do a shift and then sign extend, but we're going to do sign extend first.
What's the square versus the other line?
I'm going to send it.
What's the square
up
versus the
here.
other line?
Sequential combination.
That's going to do a shift left I'm sorry, I should have said this first. Subtract RT from RS. Those paths already exist because they're the same as the R type. If you look at the machine code format, RT and RS are stored in the exact same places that they would have been stored for the R type instruction. So that path already exists, so we don't need to add anything for that. The result is 0, we'll worry about that later. So shift label is something we do need to add. So the label is coming here, it gets sign extended, it gets shifted, and then we ought to add that to the PC. We cannot add it on the ALU because the ALU is going to use for something else. So we're going to add it to the PC using a different adder. So we're going to create a new adder, and we're going to do it that way. And what are we bringing in here? We're bringing in the PC into this input. So we'll slide this over. We don't need memory for this, so let's we'll not worry about the memory part. Let's just worry about the PC part. If you remember from the machine code, what was stored in the machine code is actually the offset from the next instruction. So we're going to bring this here, and we're going to add that to the PC. And I'm going to do this in yellow because this will change. Yes.
The sign up stand, included the app.
Yes.
It looks like, maybe I'm wrong, it's coming from the sign extend where we did to.
Yeah, because this is a 16-bit label, so we have to do the 16-bit label, so you have to do both the, you have to do both the sign extend and convert the word address to the byte address.
We're converting the word address to byte address. Is that what's happening over at the address or?
That's the shift,
Oh,
because that's multiplying by 4.
oh, that's a shift.
Thought you said
Yeah, SH left 2. Sorry. And now we got the branch and
I have
equal.
blue and red.
The result is 0. That has to do with control, so we'll talk about that later. But the data set, we did this, and we got it back.
Low income parents.
Oh,
The input for your second adder on the right, isn't that PC plus 4?
Yes.
So when,
Well, if you look at the, we kind of glossed over it, but when we did the machine code, the offset we stored was actually the offset from the next instruction. That's why we did it that way. But at that time, it's too early to tell you the reasons. So I just said, trust me, and we do it this way. But that is what we did. When we counted from the next instruction.
did you hear a
Okay, so now we have the branch unequal.
actually come up out?
Where?
It's not how it's supposed to look like.
Yes, because this is a word offset. A word offset, remember, a word is 4 bytes. So a word offset to convert it to a byte address, you need to multiply it by 4. And that is what this
This
should
is what
be.
my haircut's supposed to look like. Makeshift, this is my head.
We're multiplying the offset by 4 before adding it to the
Supposed to
PC.
look like. That's the haircut that I have.
And if it's not obvious, we'll make some examples with an actual 32-bit value
It's cute
and
though, it's like
and a
kind of
word
like-
offset, and it'll be obvious. Yes.
is it to assume that all the lines connecting to PC are yellow because there's gonna be like a larger box later?
Yes. Actually, there's gonna be 2 boxes.
I got you.
Okay. But you don't know that yet. Okay, so instead of doing the jump, I'm going to throw out the entire CPU.
Ruh-roh.
And one of you asked earlier, first let me zoom in, and then I'll
It
look
is.
it up in the book and tell you.
Teacher all that way, you want to remember.
There it is.
Oh, he
Somebody
said it was
asked
the
earlier
most
which
important
book
class,
it
and
is.
you have your headphones in and
Incidentally, I will
freaking.
post this bigger
think I didn't know.
on Blackboard.
I'm looking up.
So you don't, so you can print out.
You're looking up once every
Oh, I
5
should
minutes.
tell you, in the future, future classes, you want to print out a few copies, because we'll be marking this up a lot. So print out a few copies of this and bring it to class, because otherwise you will not be, well, you're more than welcome to copy down this entire figure every time, but you don't want to do that.
Maybe because you have a jacket
This
and a hoodie.
figure happens to be,
It's like so thin. Discounted the shirt.
Maybe it's because you have a jacket.
And I don't want to take it off and put it back on.
Yeah. The girl's been sweating.
Yeah.
okay, figure 424 is probably the best one. Wait, please.
Crazy.
But anyway, I will be, but this is the version from an earlier
That guy's
edition,
looking crazy.
which fits nicer on the screen. So I'll be putting this on Blackboard. So they,
Wait, Paul, let me draw something on it.
and you want to make, again, you want to make several printouts before you come to class. Okay, so let's talk about this figure. And then so what have we
I
done?
have random things everywhere.
We have this not only has the Lord Shorebird branch and the hard type, but it also has a jump. So I'll just show you the jump instead of writing it out in English. The jump, what does the jump do? You have this 26-bit field offset. That is bits 0 through 25 of the, let me make a fine pointer. That is bits 0 through 25 of the instruction, right there. What do you do with that 26 bits? Yeah, the jump is the offset, it's a word offset, not a byte offset, so you shift it left to, convert it to bytes. You get 28 bits. And then you append the cut the chatter, please. You append the 4 bits from the 4 most significant bits from the PC to make a 32-bit number. So you get the, from the PC, you get bits 31 through 28. You get 28 bits of the byte version of that 26-bit offset. You append that, you get a 32-bit number, and that is the resulting jump address. Now somebody already said, they said you have yellow part in the previous diagram because of muxes? Yes, because what are the choices for going into a PC? You get either PC plus 4, this one, or the stuff that we did for branch, this one, or the stuff that's coming from the jump mux, from the jump logic, which is this one. So you pick this, or this. Yeah, now Hennessy and Patterson happened to do it using 2 muxes, but we could have done it using 1 3-to-1 mux. And that the result of those muxes goes into the PC. And this is that easy. This is the moment that that you see the beauty of our CPU. It is in one day we designed a complete CPU. The data pad, we haven't done the control pad, but that is for next time. But in one day we designed the complete CPU data pad. All we did again, we wrote down in precise English, and then we figured out the combinational elements, the sequential elements, and then just started connecting lines.
And then these people, the controls.
Okay? So that's it for today.